Hey everyone. So today we're going to be looking at trends in physical properties of different organic or compound series. So we're going to examine some differences as we increase in the homologous series, which we studied previously, as well as what happens when we switch up the functional groups. But before we jump into this, we have to do a quick review of the intermolecular forces. These are the forces that govern the physical properties that we're going to study. So the weakest of the forces, we have London dispersion. So remember, London dispersion, which we also call an induced dipole force, happens when the electrons within an atom move to the side. So you can imagine the electrons they're all randomly moving, happen to gather up on one side of the atom, which causes a charge displacement. So we get a dipole with the more partially negative end being to the left and the partially positive being to the right. What this happens is the other molecules around it, this induces a dipole in them. So it pushes the electrons to this side, creating this positive-negative dipole. And on the other side, it pulls the electrons toward the positive center of the center one, again creating a dipole. And then these dipoles are attracted to one another, creating what we call that London dispersion force. Now, it's only a temporary dipole, so it's a very, very weak force, but it is strong enough to make some vast differences in physical properties. The next one in the intermolecular forces we looked at was dipole-dipole. So this is so again, London dispersion was a temporary dipole. Dipole-dipole is when we have a molecule with a permanent dipole in place. So we have to have a polar molecule. In this case, example is HCl, hydrogen chloride if it's a gas, or hydrochloric acid. So we have our chlorine, which is the more electronegative atom. So the electrons will tend to gather around the chlorine. Okay, and then the other hydrogen, so the positive center on this hydrogen, or the positive end of the dipole, is attracted to the negative end of the dipole on the other HCl. So dipole-dipole forces are quite a bit stronger than London dispersion because they are permanent forces. And the strongest of these intermolecular forces are hydrogen bonding. Hydrogen bonding are more or less just a stronger version of the dipole-dipole. So we have to have a molecule with a permanent dipole present, but that molecule, to be classified as hydrogen bonding, must have an oxygen attached directly to a nitrogen, a hydrogen, or nitrogen, oxygen, or fluorine. Okay, if it has a hydrogen attached directly to one of those, like in water, then we will have hydrogen bonding present, which, due to the charge separation between hydrogen and those three other elements, we get a very strong dipole created, so we get a very strong attraction. So we're going to tie these intermolecular forces into studying the physical property of organic compounds, starting with volatility. Okay, so volatility is a measure of how easily a substance evaporates. A highly volatile substance has a low boiling point and evaporates quite easily. Okay, so let's take a look back at our homologous series here. So remember, we discussed in a previous video, we have methane to butane, and the forces of attraction between these are all nonpolar substances, so there's no dipole-dipole interaction, there's no hydrogen bonding interaction. These are all interacting intermolecularly through London dispersion forces. Okay, so London dispersion, remember, London dispersion forces increase and get stronger with the molecular mass of the molecule. As the molecular mass increases, the more electrons you have present and the stronger the London dispersion forces will be. So as we go up this chain from methane to butane, the methane would be the most volatile and the butane would be the least volatile. So it's much harder to turn butane into a gas than it is methane. And as we increase the chain, you'll see that this trend continues. So it gets harder and harder, higher and higher boiling points as you add more carbons to these chains. Now, it's not only the length of the chain, though, that tells us about the volatility, but also the shape of the chain. So if we add some branching groups in here, for example, here's two isomers of pentane. We have pentane, which is a straight chain alkane, And we have 2,2-dimethylpropane, which is an isomer of pentane but is a branch chain alkane. Okay, look at the boiling points, 36 for pentane and 10 for 2,2-dimethylpropane. Now both of these have the exact same molar mass, okay, the same molecular formula, but a different structure. Now, the reason pentane is so much higher is these London dispersion forces have to act from atom to atom within a molecule. So these two pentanes can lie almost side by side. So we get interactions. Okay, hydrogens don't have a lot of electrons, so we don't really see London dispersion forces between hydrogen atoms, but between the carbons, we get interactions at essentially 5 different locations for those London dispersion forces. Okay, we get the carbon within the carbon atom within each one. Again, it would create the electrons move to one side. It creates the temporary dipole, which then induces a temporary dipole in the other carbon atom. Okay, so we see multiple interactions here. Now, with the branch chain one, although it has the same molecular mass, we're not getting those interactions. We're getting these can't, because of their shape, they can't line up. And remember, these shapes would actually be tetrahedral. They're not flat in the plane, but they can't line up with each other. So we only end up getting a couple of interactions rather than the many we get with the straight chain alkanes. So branch chain alkanes will have lower boiling points than an equal mass straight chain alkane. So lastly is functional groups. So now that we're adding in functional groups, we have to look at the different types of intermolecular forces. So the weakest of all of them is the alkane here at the bottom, and there's only London. Now there's London dispersion forces present in every molecule, every atom that exists, but they are only present. There's no other forces in alkanes except London dispersion. Okay, next we move up to the halogenoalkanes. Again, now we can have a polar molecule with a permanent dipole present toward the halogen group. Okay, so these have a little bit of a higher boiling point compared to its similar alkane. Now it is important, this note at the bottom here, when making boiling point comparisons based on functional groups, it is important to compare molecules with similar molar masses. This way we can rule out just having a really long chain and London dispersion taking precedence. So we're going to consider things with similar molar masses when we talk up here. So for halogenoalkane, next we have our aldehydes and our ketones. Okay, so aldehydes and ketones would both have very similar volatility. They have a permanent dipole present. Remember, an aldehyde is when we have our double bonded O on the end of a carbon chain, and a ketone is when we have our double bonded oxygen, or we also can call these carbonyl groups, in the middle of the carbon chain. Okay, so both of these have dipole-dipole forces present, so their volatility is a little less than alkanes and halogenoalkanes. The dipole is a little bigger than a halogenoalkane. Next, we move into our three that have hydrogen bonding. So our amines have nitrogen attached directly to a hydrogen. We do have hydrogen bonding, which is what puts this the boiling point higher than the other 4 previous groups. Alcohols, so the OH bond creates a stronger dipole than the NH, leading to a higher attraction. And lastly, carboxylic acid, in which case we have COO and an OH. So in this case, we have a permanent dipole in the carbon double bonded oxygen, as well as hydrogen bonding from the alcohol group on the end, or the hydroxyl group. Okay, so carboxylic acids, comparative of similar size of all the other ones, will have the highest boiling point of any of the functional groups. Okay, so again, alkanes, just London dispersion, has the lowest boiling point, weakest intermolecular forces. We move through our dipole-dipole interactions. They're kind of in the middle with boiling point. And then our highest boiling points and strongest intermolecular forces are hydrogen bonding. Lastly, we're going to take a look at solubility. Okay, so solubility is the ability of a solute to be dissolved in a solvent. So normally we're working with, say, salt and water. Okay, and we can look at different ionic compounds and how soluble they are in water. Now we're going to examine the solubility of organics. So the solubility of organic compounds in water depends on two important factors. One is the functional group that's present, and one is the length of the carbon chain. Okay, so with the functional groups, any molecules that can form hydrogen bonding are more soluble in water. For example, ethanol. We consider ethanol to be completely 100%. In fact, we consider methanol, ethanol, and propanol to be 100% completely soluble in water. And it's because these OH groups, okay, can interact through hydrogen bonding with the water, allowing the water to dissolve them. Some very short chain ketones, okay, will be at least slightly soluble in water. They do have a polar group, so if it's polar, water being polar will dissolve other polar things. Okay, so likes dissolve likes is what we say. So something that's polar dissolves something that's polar, something that's nonpolar dissolves something nonpolar. Carboxylic acids, for example, ethanoic acid, again, we consider these to be 100% soluble in water. So anything that is polar will generally dissolve in water. Anything that can, not just polar, but anything that can form hydrogen bonding with the water will be soluble in water. So again, that gives us the alcohols, carboxylic acids. They both form hydrogen bonding. Some amines, and then some that will be slightly soluble. So these ones are all fully soluble. Then the slightly soluble ones, we have the aldehydes, ketones, and some, I'll just leave it there, our aldehydes and our ketones. Okay, so we'll talk about other ones later on in more detail, like esters and ethers and how they are which ones of those are soluble and that. But today we're sticking with the main ones that you guys need to know for your exam. Okay, so secondly, the longer the carbon chain, the more hydrophobic a molecule. So up here I mentioned that methanol, ethanol, and propanol were all soluble in water, but as we get larger, they're not. And that's due to the fact that the more carbons we have, the more nonpolar section of our molecule. So for example, if we draw here, let's see, 1, 2, 3, 4, 5, 6. So if we draw pentanol, so I should say 1, 2, 3, 4, 5, and then the 6 is the oxygen. So if we draw pentanol, okay, pentanol won't be soluble in water. So this piece, let me change here. So here is where we can perform hydrogen bonding. But the rest of this is nonpolar. Okay, so this nonpolar, we call it hydrophobic, whereas the polar part, we call it hygroscopic. Okay, so this nonpolar piece, the carbon and hydrogen, the long carbon chain, prevents this molecule from being soluble. Okay, because water can only interact with the alcohol group on the top here. So the longer the carbon chain, the less soluble a molecule will be, regardless of the functional group that's on it. Now for you guys that are in biology, this may look slightly similar. You may have seen this thing before. And then, okay, so this is just a side note for the biologists that are listening in. So you may have seen this when you're studying the cell. So this we call the phospholipid bilayer. When you're actually drawing this, it's not just heads and tails as it's discussed, but that head is actually a polar molecule. So I believe it's some phosphorus attached to possibly a nitrogen up here. I can't remember the exact structure, and then attached to a long carbon chain that zigzags down. Okay, this top piece is your part that can perform hydrogen bonding. This is your hydrophilic part that or your water-loving piece, whereas we have the water-fearing, the hydrophobic tail, which is all just carbons and hydrogens going down, and this creates your phospholipid bilayer in the cell. So it is just a long carbon chain that's creating this separation.